Let's talk about NFTs next, non-fungible tokens. That is, tokens that can only exist once, where there's only one coin in existence. The examples of native tokens that we have studied so far are definitely not NFTs, because we could easily mint as many as we wanted of those. Both in the first example, where minting was totally uncontrolled, but also in the second. As long as you are the owner of the specified public key hash, you can mint as many tokens as you like. Now, in order to produce an NFT, maybe the first naive idea would be to actually, in the policy, look at the TX-info mint field, which we haven't done so far. All we did look at in the last example was the signatories of the transaction. But if we actually look at the TX-info mint field, we could add a condition to the policy that the forged value has an amount of 1. But that wouldn't help us. That would only mean that during one transaction, you can only mint one token. But nobody could stop us from submitting as many of these transactions as we like, and then again mint arbitrarily many tokens. So that won't do. That won't enable us to guarantee that a given token can only exist once. A second option that has been possible since the Mary era, which predated the Alonso era that brought us Plutus, is to use deadlines. So we saw in previous examples, in previous lectures, how time can be incorporated into Plutus script. And we can do the same, of course, in policy scripts. So the idea here would be to have a deadline that only allows minting before the deadline has passed. Then if you want to do an NFT, you mint one coin before the deadline has passed and then allow the deadline to pass. And then it's guaranteed that after the deadline, no new tokens will ever be minted. But in order to check that before the deadline you only minted one, you need something like a blockchain explorer. You must check on the blockchain that only one of these tokens was ever minted before the deadline. You're guaranteed that after the deadline, no new ones can be minted, but in order to make sure that only one was minted before the deadline, you actually have to check with the blockchain explorer. So in that sense, the NFTs that use this Mary era deadline mechanism are not true NFTs in the sense that the currency symbol by itself guarantees that they are NFTs. In order to check that only one exists, you have to look on the blockchain. Now, using Plutus, it's actually possible to mint true NFTs, where if you know the policy script that corresponds to the currency symbol, you can be sure that only one such coin can be in existence without having to resort to something like a blockchain explorer. And if you think about how to do that, you must prevent from there ever being more than one minting transaction for the token in question. So whatever you write in your policy script, it must only result in true for one transaction. And it must be impossible to do the same again in another transaction. And at first, that sounds impossible, because why can't you simply do the same transaction again later, and then validation should again succeed, and it should be possible to mint token again. At least if you do it in the same slot. I mean, we mentioned deadlines before, so of course time plays a role. But why can't you simply at one slot issue the same transaction several times? And the key here is that we need something that's unique. We need something on the Cardano blockchain that we can refer to in our minting policy that is unique, that can only exist in one transaction and never again. And that is a very important trick, something to keep in mind. And the idea is to use UTXOs, because for the reason how UTXO works, UTXOs can only exist once. Every UTXO is unique. You can never have the same UTXO again. A UTXO is there, and at some point it may be consumed as input to a transaction, and there can never ever be the same UTXO again later in the life of the blockchain. Of course, there could be another UTXO that goes to the same address and has the same value and has the same datum, but that will still not be the same UTXO in the sense it will have a different ID. So what is the ID of a UTXO? Well, a UTXO is the output of a transaction. So in order to pinpoint a specific UTXO, you must pinpoint the transaction it came from via its transaction ID, and you must say which output of that transaction it was. The outputs of a transaction are ordered, so by specifying the transaction that produced it and saying which item it was in the list of outputs, you can uniquely identify an UTXO. And transactions are unique. There can never be the same transaction again. And because transaction and index determine the UTXO, this implies that UTXOs are also unique. So now, of course, you can ask, why are transactions unique? And that is a bit subtle, because they wouldn't be unique necessarily if it wasn't for fees. If it wasn't for fees, you could have a transaction that has 0 inputs and only outputs without value. So transactions with no inputs and outputs where each output doesn't have a value. Such a transaction could exist several times. You could have the exact same transaction and it would have the exact same hash and hence the exact same transaction ID. But in a system with fees like Cardano, you can't have such a transaction because you always need an input that provides the fees to pay the transaction fees for the transaction. And as soon as you have an input, that input must come from somewhere. It must come from a previous UTXO. So basically, by a simple induction argument, you see that as soon as you have fees, transactions can never be repeated. You can never have two identical transactions in the sense that they have the same transaction ID, because they must spend fees, and these fees, because double spending is impossible, must be different UTXOs for different transactions, and the inputs are incorporated into the transaction hash. So if you have two transactions with different inputs, those two transactions also will have different transaction IDs. So that means that every transaction in the history of the blockchain is unique, has a unique ID, and that implies that also every UTXO in the blockchain has a different ID, a different combination of transaction ID and index. And this is a very important fact, and that is a fact that we can use in order to create true NFTs. So the idea here is to name a specific UTXO as parameter to our minting policy. And then in the policy, check that the transaction that does the minting consumes this specific UTXO. And because of what we just said, once a UTXO has been consumed in this transaction, it can never exist again. So there can't be another transaction that consumes the same UTXO. And this strategy guarantees that with a minting policy like that, there can only ever be one transaction that consumes this UTXO. And that is what we want to achieve in order to guarantee that we have a true NFT that can only be minted once. In order to demonstrate that, let's look at the last example for today's lecture in module NFT. So now our script will be parameterized by two parameters, the token name and a TX outref. And the condition will be that we mint exactly one coin with this token name and that the minting transaction consumes this TX outref. And as I just explained, this will guarantee that there will only ever be one coin with this currency symbol, the currency symbol given by applying these two parameters to this script. So there are two conditions we have to check, namely that the specified UTXO has indeed been consumed by the transaction. So this will be done in the helper function has UTXO. And if that's not the case, we log the error message UTXO not consumed, and that we mint the exact right amount. So exactly one coin with this token name and amount 1. Otherwise, we give this error message wrong amount minted. So we extract the TX info. Now for has UTXO, we use any. So any is a very useful function from the Haskell prelude, given any container. So you can think lists of A's, and a predicate on A's checks whether there is at least one element in this container, element in this list, where this predicate is true. So apply that to the TX info inputs, which is the list of all inputs to the transaction. And the predicate is given an input, we check whether the TX in info outref, which is exactly the ID of the input, the ID of the UTXO we are consuming, is the given one. So this will be true if there is an input that corresponds exactly to this TX outref. For the second condition, check minted amount, we make use of the flatten value function we looked at earlier when we talked about values, which converts, if you recall, this nested map into a flattened list of triples. So this is now the first minting policy where we actually look at the mint field. So we get the value that's been minted by this transaction, flatten it, and what we want is that there is exactly one triple. There is exactly one minting going on, and we call the triple as currency symbol, token name, and amount. We don't care about the currency symbol because we know the currency symbol will be the one we are checking right now. Otherwise, this minting script wouldn't be executed. Remember, I explained how validation in the presence of minting works. So if there is a non-zero coin being minted or burned, then the corresponding script corresponding to the currency symbol of that coin will be executed. So if there's only one coin being minted and we are in the process of executing the script, we know it's this currency symbol, the one that corresponds to the script we are writing just now. So I must check that the token name is the one given by the parameter and that the amount is 1. So we are minting or burning exactly one coin, and that has the right token name and it has the amount 1. So now we have to convert this again into an untyped version. So again, for reasons of making it easier to work with in Lucid, I did something unusual that I normally wouldn't do. So normally I would just, again, have two parameters here, one of type TX_outref, one of type token name. Now I changed that into 3 parameters, all of type built-in data. The idea is that TX_outref actually is a record type where the first field is a transaction hash, the transaction ID, and the second field is the index. So recall a UTXO is given by the transaction that produced it, transaction ID, and then the index of the output in that transaction. So these 3 parameters, the third one is the token name, but the first one is basically the transaction hash, and the second one is the index of the output. So it's easier to work with that in Lucid if I split it into 2 separate parameters. So these first 2 correspond to the TX_outref here. So given a transaction ID, which is now serialized as built-in data, so it's just a string, and an index, which is just an int, and a token name, which is also just a string, I first compute the corresponding TX_outref. So I take this built-in data, deserialize it as a string, and apply the transaction ID constructor to it. So transaction ID is just a new type wrapper around built-in byte string. For the index, I just deserialize it. to get the int, and then I have my TX outref. Token name, I just deserialize the token name. So this is a bit weird and I don't really understand it. So both transaction ID and token name are just new type wrappers around built-in byte string. So internally at runtime, both are represented by built-in byte string. And they just use different new type constructors, one the token name constructor, one the TXID constructor. But for some reason that I don't really understand, the serialization to built-in data is different. So in the case of token name, the string or byte string constructor of data is used. Whereas in the case of transaction ID, there's an additional layer of indirection. So there it's an object which uses a constructor with one field, and that field is a built-in byte string. I have no idea why these two types that are very similar, both new type wrappers around built-in byte strings, are serialized differently. But because of that, it looks a bit different, my treatment of the transaction ID and my treatment of the token name. But the idea is, so this will be a string, this will be a number, this will be a string. And then I take that string and that number and assemble those to a TX outref. And I take that string and convert it to a token name. And then I can use my typed version of the policy. And as I said, all this complication is only necessary because I want to make my life easier in Lucid when I apply the parameters. So if you didn't use Lucid, if you use something else, then all of this wouldn't be necessary and you could just use TX outref and token name here as well and only use 2 parameters instead of 3. Okay, and then the rest is just standard. So again, I split this compilation and parameter application into 2 parts. So this is the parameterized script, which is not yet a minting policy because the 3 parameters haven't been applied. So it's just compiled code. And then if I want an actual policy, I can use this compiled code and apply the 3 parameters. So here I do the opposite to what I did here. I take my outref and extract the transaction ID and unwrap it from the TXID constructor. And I take the index. And for the token name, I don't first have to unwrap it and can immediately serialize it to built-in data. As I said, I don't know why these two types are treated differently. It's just the way it's implemented. And then I have my helper functions for serialization. So if you want a specific minting policy where you already know the TX outref and the token name, you can use this and you end up with a serialized minting policy on disk. We will use this where we don't apply parameters yet. We will do that in the off-chain code. And finally, for a given TX outref and token name, a function to compute the currency symbol. I made yet another copy of the off-chain code, called it Lucid NFT. And again, the beginning is very similar. In this case, I don't need the helper function to ask for the amount because the amount will always be 1 because it's an NFT after all. So again, I initialize Lucid and I set up my wallet from my secret seed and I get my address. In this case, I don't need my pub key hash. Now I need the 2 parameters. So token name, I just fix for simplicity. I just use the token name PPP NFT. But I also need this TX outref, the input we are going to consume in the minting transaction. And of course, I could like explicitly give that, but then I would need to look on Blockchain Explorer or use the Cardano CLI to find UTXO sitting in my wallet that I actually can spend as an input. So it's easier to have Lucid take care of that automatically. So I use this Lucid function UTXOs at, so given an address that returns me a promise of an array of UTXOs. So all the UTXOs sitting at a given address. So this will give me all the UTXOs in my wallet. And I just take the first one. it doesn't matter. And I lock this, define the token name. Now for the parameters, in this case, I have three. So a string, the transaction ID of the TX outref that I am going to consume, then the index, the output index of this TX outref, and the token name. So in this case, the definition, the specification of the parameters looks like this. And to apply them, so this is what I got from executing my helper function in the Haskell code to serialize this compiled code to disk. So that's that. And now comes the array with the three parameters. So I looked up this UTXO, and that has a field TX hash, which is exactly the string I want, the first component of the TX outref. It also has a field output index. So I just have to convert that into a big int so that Lucid is happy. And finally, the token name that I defined earlier. And there I also have to, again, convert it to hexadecimal first, as before. And that's it. So now the NFT policy is saturated. So the three parameters have been applied, and it's now a specific minting policy. So the rest is as before. So I can compute the policy ID. I log it. Now my unit, asset class. Now I can construct the transaction. So these first three are as before, but now I must also make sure to actually spend that input. Recall that was just the first UTXO in my wallet, and Lucid has some sort of coin selection algorithm to pay for the fees, but it's not guaranteed that it will pick this UTXO that I specified as an input to the transaction. And I complete. I sign, I submit, and that's it. Maybe before we try it, we can again try to see what happens if I exclude this line, if I comment it first. And indeed, I get an error called error, and the error message is UTXO not consumed. Remember, that was the first error we logged in the case that the input I claim must be consumed by the minting transaction is not consumed by the minting transaction. So let me uncomment this again and try again. And now it worked. The NFT hasn't arrived yet. And there it is. Let me just run the same script again. And it worked again. And now we see that the UTXO that we picked the first time to be consumed, it starts with EEADC. And now the second time, it's a different one. That's exactly the point, this trick, how we achieve a true NFT. Because in the first minting transaction, we consumed this UTXO. So for the second, it's no longer available, and we pick a different one that we find in our wallet. So as a consequence, the minting policies and hence the currency symbols are different. So this is 202DO and this is 9318D. We wait until that second NFT also arrives. And now we have two NFTs. They do look similar, but that's just the way Nami displays these. But also Nami realizes that it's not the same coin. Otherwise, it would just say this coin with amount 2, but it separates them. So it's different coins. It's different NFTs. Actually, we can also see here in Nami, we can inspect the policies, and we see this 202D and the 9318 here as well displayed in Nami. So these are indeed two different coins, unique NFTs, which is exactly what we wanted to achieve.